morning, students. I hope you have good session in the first week. I was also going through these lectures, and I have few questions in my mind. Incidentally, we are all aware our Prime Minister occasionally or regularly, to be more precise, announces a program called Man Ki Baat. And in that, he tries to share his feeling about what is happening in and around this world, and more specifically, what is happening in this country. I also thought, let me also see all these lectures for last 1 week, and let me share with you my Man Ki Baat. And the success will be decided by the answer whether my Man Ki Baat has become your Man Ki Baat or not, right? So I give this title, Man Ki Baat. And it's basically introspection. We'll try to revisit whatever we have studied the first week, and this will be a routine feature. The new week will start with the Man Ki Baat, where we'll revisit whatever we have discussed, and whatever I feel that yes, these are the points where I should be more specific, I should give more stress. These are the area which I should not give too much of stress at this time, because we are going on pumping information to you and we don't have any eye contact with you. I don't get a feedback whether I am able to communicate or not. So it is better that we follow this practice and try to crystallize the basic foundation before we take off, right? If you go in the first session, you will find we have defined something called aerofoil, and we have realized that aerofoil is basically a 2D concept. That is, it has a contour with an infinite span. The basic message here is that we are restricting the flow to go in this cross section. There are no cross flows this way or this way, right? That means the flow will be more characterized by the contour of this aerofoil. That is, if this is the aerofoil, then the contour of the wing and the flow over the wing will be decided by this contour, and there won't be any lateral flow or cross flows, right? In that we define something called streamline. We didn't define streamline. We want to define streamline in a little bit of explicit manner, but without going much into the details. What actually happens? Suppose the fluid flow is coming like this. What happens here? Here, some fluid will go like this, some will go like this, right? And this flow over this surface, both these surfaces, will decide what is the pressure difference. Okay? Now the question comes, why at all there should be a pressure difference? This question we need to ask. We need to understand a little more. And we will be addressing that part. First, if I want to represent this flow, which direction the flow is going, one of the ways is to define streamline. What is a streamline? You imagine those points in this flow, and if I draw tangent at this point, that should give me the direction of the flow. So this becomes your streamline. This is another streamline. Okay? That is, any point you pick, draw a tangent, that should give direction of the flow. It helps in visualizing, it helps in modeling. Okay? So you can write like this. So many streamlines will be going like this. Infinite streamline I can draw, right? Because these are fictitious lines. This only helps to understand, to represent the direction of flow, nothing more than that. Okay? However, this concept you will find aerodynamics have used in developing an analytical model of relevance to understand what is the forces, how the forces are acting, what will be the force behavior with the orientation of the aerofoil, etc., etc. Right? Forgetting about streamline and all, if I draw a symmetric aerofoil, symmetric, we have defined that this distance from the chord line, they are same. Right? Though it is really not drawn properly, but I hope you understand by now what is a symmetric aerofoil. What will happen? Without going into aerodynamics or anything very specialized, by natural justice you will find the half of the flow will go like this and half of the flow will go like this, because one of the this half over a particular line flow will have a direction like this, the other part will flow go like this. So there will be another line where flow will be just like that. There won't be any flow that direction. So it separates lower as well as upper flow. This part separates upper and lower flow. I am not using any aerodynamic term. So now see one thing. If it is symmetric aerofoil, that means from here to here and from here to here, if I measure their length, they will be same. That means the flow over this, if it remains attached, it will travel from here to here, flow here will travel from here to here, and they will travel equal distance. Okay? And there is another law of justice or natural law is that whatever fluid is coming here, they have to come out. They cannot get stagnated at one point, right? They cannot get accumulated at one point, which we call the continuity of the fluid particle motion, right? That is, if we try to draw a pipe, if I allow fluid to flow through the pipe, I know that whatever is going here has to come out. Okay? If that is true, that means if they are traveling equal distance, upper portion as well as lower portion, that means they will have same average velocity. And if the velocity is, average velocity is same, that means the pressure here and pressure lower has to be same. Because you know Bernoulli's P plus half rho v square has to be constant, right? And since both are having same average velocity, so the pressure remains same, so the pressure upper and pressure lower will be same, and hence there won't be any lift. This is one of the explanations. Okay? There are many explanations, and explanations are designed, are formulated to suit mathematical modeling. So you'll see there are many ways of defining this other than what I am explaining here. This is using the very fundamental common sense. Okay? Now think of if this same symmetric aerofoil is at an angle of attack, alpha. Now the question comes, what is angle of attack? To understand what is angle of attack, again revisit, if this is the plate, okay, and if this is the velocity direction, I am concentrating on the vertical plane, okay? And vertical plane, whatever the angle between this velocity vector and the chord of the wing is called the angle of attack, okay? Now what happens if I try to visualize like this? What you could see that flow will something go like this and some flow will go like this. What is the difference between this picture and this picture? Now you could see that the upper part of this fluid, they will be traveling more distance than the lower fluid. Am I correct? This is going like this, so it will be traversing larger distance than this fluid particle. However, because of continuity, whatever has entered here has to come at the same time, that is fluid particle all will come at the same time here. That also tells us, since this is to travel larger distance, the average velocity here has to be greater than the average velocity lower, or I call it upper. Is this clear? If it is at angle of attack, now I could see this fluid stream has to traverse larger distance compared to the lower part of the fluid. However, all the fluid has to come at the same time. That means the upper part has to hurry up because larger distance. As it hurry up means I say the average velocity of the top surface will be higher compared to the lower surface. And if upper part speed is higher, and we know that P plus half rho v square is constant, that is the Bernoulli's theorem. So if this man is higher, that means this man has to go down. If this increases, this has to go down. That is why the pressure here reduces. Pressure upper now goes down compared to pressure lower, or I say pressure lower is greater than pressure upper, so there is a lift. Is this clear? Okay. I have purposely avoided technical term which an aerodynamist will use. They will define something called stagnation point. I am not using those things, right? Okay. Then we were discussing about cambered aerofoil. And now that symmetry has been broken. Now what happens? You could see here from this geometry, if the flow is coming like this part has to have higher speed compared to the lower part. Same theory will apply here, and we will have pressure difference and we will have lift. Okay. We also realized that if I plot CL versus alpha for a symmetric aerofoil, up to certain point it is linear, and after we call it here, strictly speaking, we call it CL max, that is the maximum CL this wing or this aerofoil can generate, and after that there is a drop in CL, increase in drag, and that area we call stall. So conventionally we call this angle at which the flow separates, we call alpha stall. So these two important terms, one is alpha stall, but you could see also at alpha stall CL is CL maximum. That means if you further increase the angle of attack beyond this alpha stall, you will not get additional CL. In fact, CL will reduce. This is the additional thing we should also understand. And for a cambered aerofoil, you will find this graph is no more like this. It is like this, where at this I write cambered, and you see at alpha equal to 0. For a symmetric case, CL was 0, but for cambered, there is a positive value which is called denoted as CL naught. And if I extrapolate this point, you find here alpha for CL equal to 0, and which is negative. You could see here, if I am flying at this alpha, then the CL is 0 and this alpha is negative, right? Okay. This is very important. It is also denoted at alpha 0L. Many textbooks you will find like that. Okay. For cambered aerofoil, I get larger CL at smaller geometric angle of attack, but at the cost of what? The alpha stall reduces. So although we are getting this CL more, however, alpha stall will reduce. If this is a cambered aerofoil and this is alpha for CL equal to 0, right, which is negative, and if I draw a cambered aerofoil, I know there is a zero lift line, that is, this is called zero lift line. That means if the flow comes like this, that is at a negative angle of attack, how much? Corresponding to this alpha CL. If the flow comes like this, then there won't be any CL generated by the cambered aerofoil. Right? In flight mechanics, we use this concept more frequently when we are discussing about stability and control. I repeat this. You could see that this is a negative angle of attack, because positive angle of attack is when a flow is coming like this. This is positive angle of attack. When I draw like this, it's a relative here. The airplane is actually going like this. Okay? Okay? Right. But negative will be in the reverse direction. That is why this is negative angle of attack. Okay? So this was what we discussed, or we create a foundation. I'm trying to add a little bit of more insight into it so that our next lectures become very smooth. After this, from aerofoil, then we try to talk about wing, and we talk about finite wing, talk about finite wing, and we realized finite wing means this span is not infinite, it is finite. So at the tip of the wing here, because there is a pressure difference in the bottom and the top, there will be vortices, or they will draw kinetic energy, rotational kinetic energy, at the cost of the machine energy. So there is a drag, and we call vortex drag. So if I draw it like this, something like this. So this is vortex drag. It is also called lift, induced drag, or sometimes simply induced drag. Right. And we realize that if this span, which is this B, becomes infinity, then this vortex drag will not be there, because there won't be any physical pressure difference. So the vortex drag or induced drag will be 0, and that is like you are approaching towards an aerofoil, which is two-dimensional, right? And there we define something called aspect ratio. And we define aspect ratio as, if this is the span, and if this is the chord, then aspect ratio was defined as B square by area of wing. That is the aspect ratio of the wing. If I want to calculate aspect ratio of the tail, then span square, tail span square by area of the tail, right? For a rectangular wing, it becomes B by C. However, if the wing is something like this, then actually you have to find out the area of the wing, which will be here, and span square divided by area of the wing will become your aspect ratio. Then it will not be B by C, because C is changing. Chord at every point is changing. While discussing induced drag, we very lightly mentioned something about lift distribution. We talked about elliptic lift distribution where the induced drag will be minimum, and the lift distribution was typically something like this, where if you see here, there are no pressure differences, right? But in actual practice, what will happen, it may be something like this, okay? The best way, of course, I should not draw it something like this, okay? But it may change. It will not be elliptical. The best way to approach towards elliptical distribution is that you give the wing this sort of a configuration where I call this as CT, which is the tip chord, and this I define as CR, which is the root chord, and I define taper ratio as CT by CR. And if I keep this value 0.4 to 0.5, for all practical purpose, I am approaching towards elliptic distribution. Not elliptic, but yes, towards elliptic distribution. Okay? That you could see that we are making here the area less. So we are discouraging lift at the tip. But let us come back here. As a designer, I will like to reduce this effect. So what do I do? One of the most popular way of doing it is, we know that because of the pressure difference, physical pressure difference between bottom and the top surface, there is a flow like this. So what do? We discourage them to come from bottom to top, right? And this is the basic concept behind winglets. You'll find many airplanes will have winglets. That is, you put some surface here. There are many variants of design for designing winglets. But the concept is, by putting this, you are physically separating these two portions, bottom and the top, so that there are less vortex. Okay? So the winglets is the concept that is used. There are many other concepts that is used. You can put aerofoil at the tip which are not that lift effective. You can destroy that contour so that you are destroying the lift generation at that point, and that way the pressure difference at that point will be less. So you are expected to get less vortex drag, okay, or induced drag. Okay, this another thing on aspect ratio. How I was sharing with you, how I understood. If you see George Calais' explanation that you need angle between the surface and the velocity vector, definitely there's area. So I was asking question, if I put this, both are having same area. So how do we distinguish this? Now, we know by now that I would like to put the wing like this, not like this, okay? How I understand is, see, remember one thing, whole lift distribution which comes because of aerofoil, this is the region here where I explained you the flow accelerates and there's a drop in the pressure. Mostly this portion is responsible for generating the lift in a dominant way, okay? So if I put a wing like this, I can think it has large number of aerofoil, okay? But if I put like this, then I have got a smaller number of aerofoil. Anyway, because the top portion, front portion is going to contribute more towards lift. So that is why I see that aspect ratio should be clearly understood and its importance. Then we were having a session where our quality control manager Rekha Sharma was physically demonstrating you the components of airplane and their role, okay? And this was wing, Okay? And we by now know this is aileron. These are flaps. In fact, all these components are flaps only. It is for a specific purpose we are giving a name to this portion as aileron, and this is a flap. The role of aileron is what? Question is this. Suppose imagine this is the wing, and I am putting this aileron down and this aileron up. What will happen? The moment I put the aileron down, this wing camber will increase, so its lift will increase, and this will go down, so it will turn like this. So this aileron, a pair of aileron is used for banking the airplane. Okay? So aileron is for banking, right? Or sometime for roll also, it is referred to. Then we have got, this is the elevator. Okay? What the elevator will do? Imagine this is the horizontal tail, okay? And part of it is the elevator. So I am moving in this direction. If I put the elevator down, what will happen? Again you see the camber is changed, and as per George Calais, now this portion is having an angle, but I will explain with as if the camber has changed, so the lift will increase here. As the lift increases here, CG is in some front, so it will give a nose down moment, right? The airplane will now go down. That is, if I put the elevator down, the aircraft will go down like this. In contrast, if I put the elevator up, so now force will be downward, so the nose of the airplane will go up. We say airplane will go nose up. So to take the airplane attitude up, I will put the elevator up. To take the nose of the airplane down, I will put the elevator down. Is it clear? If I want to take it nose up, I will put the elevator up, force downward, so it goes like this. If I want to take the aircraft down, so I will put the elevator down, so this will give a force upward, and CG in front, that will take it down. Okay? So that is the primary role of elevator. Then we have rudder. Okay? Again you think like this. Suppose this is the vertical surface. Okay? See, this is the aerofoil, the vertical surface. And I am going in this direction. Now if I put this rudder towards my right, I am flying like this, so I have deflected towards right. What will happen? If I deflect towards right, then it will experience a force in this direction. That will give a yawing moment, which will take the airplane towards right. That is, if I put the rudder towards right, the airplane also will go towards right, like this. If I put it other way, towards left, the airplane will go towards left. Okay? So that is the function of rudder. Then comes here the flaps. If I take a cross section here, so it also has an aerofoil, right? And this is the flap, let's say I am drawing here. As I am putting the flap down, what is happening? What has happened? The whole camber of this section has increased, right? So the CL for a given angle of attack will increase, right? So this is the way to increase the CL max. We will see that when you talk about landing and takeoff, how to increase CL max so that I can take off at a lower speed. Okay? So this is the role of this flap. Okay? If I understand all this thing clearly, I will be able to synthesize all these things through the requirement of an airplane for a specific performance. Okay, that is why it's important to know. See, the next lecture will be on the atmosphere. Why it's important? Because whatever lift drag we are getting, that is coming out at the cost of interaction of airplane, a body, with a medium, right? So far we have been talking about the configuration of the body: aerofoil, wings, flap, fuselage, tail, elevators, etc. But since it is because of interaction of the body and the medium, we need to know the property of the medium also. So the next lecture you will find will be on atmospheric or atmosphere, right? And more precisely we'll call it standard atmosphere. Why this is the requirement? See, if you have purchased a motorcycle and somebody asks you what is the average fuel average you are getting, you say, our company told it is 50 per liter, but I am getting 35 or 40 per liter. Then you go to the company will simply say, see, the road where, or the traffic where you are or where you are driving this motorcycle is not an ideal condition. This will indeed give 50 km per liter if you are running on a highway and where there are no traffic jam, you can maintain a speed. So what actually they are telling, when I am trying to compare to motorcycle performance, I need to know that the platform where I am driving this motorcycle should be well defined. Okay? Similarly for aircraft, if I want to compare performance of two airplanes, then I need to compute, evaluate their performance characteristics when they are flying at a common or same atmospheric environment, right? And that is where this concept of standard atmosphere came into picture. You will see that we will try to develop methodology, which are already established methodology based on experimental results and with an assumption that air behaves like a perfect gas. That is, we will assume that P equal to rho RT valid for this, and we will try to give a description of pressure, density and temperature as we are going higher and higher. The approach will be, I will be knowing the condition at sea level. As I go up, how the pressure is changing, how the density is changing, how the temperature profile with altitude is measured experimentally. And we'll be using this to give a description of pressure, density and temperature. Right? And also please understand, when I'm trying to find the pressure change as I'm going higher and higher, I need to also know few things about altitude, because if this is Earth, this is Earth center, if I call it radius of Earth, then at any point P, if I try to define the distance with respect to the center, let's say it's HA, which is traditionally called absolute altitude. This has more relevance in space flight, right? Because there is an interplanetary motion, the value of G changes drastically. But when I'm talking about atmosphere, I'll be talking about atmosphere which is present within certain definite altitude measured from the sea level. Okay? There are no atmosphere here. So that time if I use this altitude, I'll be doing a wrong modeling. Okay? So that is why there is another altitude is defined, which is defined as Hg, which is measured from the surface of the Earth, or more critically, if you want to be correct, you say from the sea level condition. Right? So this is your Hg. We'll be using this concept, and we'll see that if I am around 60 kilometers altitude, Hg and the new height will be defining, there's a compulsion to define new height, which we'll be calling as fictitious height or geopotential height, because as I'm going higher and higher, please understand the pressure is because of the weight of the fluid, okay? And how we will be computing pressure? We know the pressure at sea level, and as I go higher and higher, I'll try to find out what is the change in the pressure. That is dP, which is negative, change in the pressure. So change in the pressure has relation with the weight of the fluid, and weight means is G, local value of G, which changes with height, which changes with height measured from the center of the earth. So there is a complication. There are some simplification will be made as long as we are within 60 kilometers. And this is what will be required to describe the pressure, density, temperature in an atmosphere, which we will be calling standard atmosphere, and we will be also defining the standard atmosphere initial conditions, that at sea level, when I say standard atmosphere, what are the value of density, temperature, and pressure. And then through the table, I can know the standard value of pressure, density, and temperature at any altitude, which will be used to compute the performance of different airplane, or if you want to compare the performance, some internal test results, then I can use those values also and corroborate. Okay? So next lecture will be on standard atmosphere.